So I think David's up first. Is he here? There you go. Jeez. Sleeping on the job already. So David's going to do a short presentation, and if you guys could hang on to your questions, if you have any, until afterwards. We'll give you some time afterwards. Okay? David, it's all yours.
Can you get the last? And then drag
Yes,
this
for sure.
for me? Thanks, Chris.
I got a mouse here.
Okay.
Pointer if you need it. This one right here?
Yep.
Okay.
You can throw me out after 10 minutes because that's what I agreed to limit this to. I got 14 slides. I'd like to introduce something that some of you are aware of.
So here, I'm going to play slideshow, and you can just scroll to go to the
Can you
next slide.
fill screen it?
Yep.
Good deal.
And then, yeah, there's the scroll.
And that makes it go next slide?
Yeah.
Perfect. I'm more involved in tech on the air side courses. We have the principles of moving air, ventilation, and forced air. The forced air guidelines is really a duct sizing course. Heat loss, appliance selection, duct sizing. What I'd like to do is introduce you to the concept of duct design, which is the principles of moving air. This course was started 10 years ago. It was taught to about 150 people, but it got to the point it needed revision, so it's taken 2 years of labor of love to put it together. We got 100 photographs. We have Gary Milligan and I've been working on this for 2 years. We got 100 photographs, 150 charts, graphed, and illustrations, trying to make it a picture book. The front part of the book, which the course is revolved around, is 55 pages. There's an appendix of 45 pages, which is useful information to know. The intention is to explain the whys and the wherefores of the quality first. Quality first is a wonderful standard. Whenever I'm doing any kind of duct design, it's absolutely wonderful. But what this does, it gives you the understanding of what's behind it, and I'd like to go through a few slides to make that really, really clear to you today. So, this is fast. So the difference is, duct sizing is still strong. It's being revised right now, but it's a great way to size duct systems for a forced air heating system once you've selected that appliance. This is the whys and the wherefores, and the question is, why is the principles of moving air important today where it may not be a few years ago? I have one slide that I think will convince you unequivocally why it's important today. What you may not have thought about is that not too long ago we had furnaces that were quite happy running between 70 degrees and 90 degree temperature rise as the difference between what was sucked in the cold air return grill and what was coming out of the supply grills. These furnaces ran quite warm, and that was their sweet spot. But what you may not have thought about is that when you had a furnace like this, it took about 12 cubic feet a minute, and it packed a hell of a wallop. You'd get 1,000 BTUs for 12 CFM. As we got to more and more efficient gas furnaces, you can see that the green bars become higher, and it takes an awful lot more air to carry that same BTU that we used to carry before. But heaven help you if you stick a heat pump into an existing gas furnace with duct system that was running at these temperature rises, in that it takes 3 times more air to carry a BTU with a geo or air source heat pump than it does to carry that same BTU with a gas furnace of 20 or 30 years ago. This is missed by an awful lot of people that are doing and that don't have enough skill to do that job properly. The principles of moving air is to try to give you some understanding of how air moves through a duct. Because ductwork system is real simple. You buy a fan, it moves air. But then against that, you've got to subtract the pressure drop, the static pressure drop incurred by the duct system, the filters, the coils, and the other things you may wish to add on. So it's simply you're buying something to move air, and then you're throwing a whole bunch of impediments into that duct system that slow it down. This is becoming serious today because the new appliances move more air. If I look at an older air-cooled furnace that has an output of 68,000, that's represented by that black appliance that stands just about 5 feet tall. If I replace it with an identical output Lennox furnace that's modern, I've got 68,000 out of this guy, I've got 67.9 in the red one, but the difference is that that new appliance makes 72% more airflow across it to do the same job. The bottom line with heating equipment, you have to scrub more air across these devices to get them to be more efficient. There's no other rules to do it. The more air you put through that furnace, the more heat you're extracting from that heat exchanger with only the smaller residual going up the chimney. Really, really simple. You can't argue with this shit. It's physics. Okay, now, Let's look at it a little bit more deeply. You take this original air-cooled furnace that was installed to a quality first standard of 0.15 external static pressure, and you compare it with this Lennox. And let's say you put the Lennox in, not to be good or bad about Lennox, this is physics. You put this appliance into this ductwork system, you have 72% more air going through it, but your static pressure, the force by which you have to push in order to get that to work, is over twice what it was before. But look what happens to your horsepower. If you were satisfactorily doing the job with a 1/6 horse, you now need almost a 1 horsepower motor to do that job. These aren't arguable. They're not negotiable. These are facts. It's called the fan laws, which is a principal part of this course. Really, really simple stuff. Oh shit, there we are. The workhorse of this whole industry is what we call a forward curved double inlet blower. And it's a simple device where you put a fan on one side, air goes around it, air goes around the other side, and it moves air because it's inexpensive, it's quiet, and it's very reliable. And quiet trumps an awful lot of stuff in residential heating and cooling. What we do get into the fact, though, that there's 5 other common fans that we use residentially, and they all have different qualities and the ability to move air. And it's important to know about these things. You have axials, which are typically used on coils in parking lots. You have a single inlet forward incline. You have backward incline fans, which are without a scroll, and some of these cross flow fans, which are being used in ductless splits. And they all have their place, but there's also places that you can't use some of them. For instance, you never use this type of a fan in a ductwork system. You're an idiot if you try. You just get a hell of a lot of noise and no performance. But there's all sorts of shit like that you can buy at Home Depot for that purpose. Okay, well, one of the things that distracts from the amount of air, that reduces the amount of air that you can move through a furnace, is fittings. And it's not really the length of the duct that matters so much and how much air you can move through a duct system, but how many corners you're smashing that air around to do it. I'd like to take one single fitting that Gary and I have learned is the single biggest culprit for reducing the airflow through a duct system in a residence, and that's the drop elbow. It's labeled as a pig because it is a pig. If you have an 8 by 32 duct, it has 50 equivalent feet of pressure drop according to just moving this air through that one sharp throat fitting. 50 equivalent feet of straight duct. So who cares how much straight duct you got when you throw something like that at it? Well, let's go back to the 1930s and look what they learned back then. Back then, all they had for technology was a fan, put little wee bubbles in it, a strobe photograph, an ASHRAE, which was published in Gary's Tuttle and Bailey catalog, probably down around the 1930s or 40s, showed what happens when you take a cross-section at the drop elbow to see how air goes around it. The air coming from the top of the drop is more or less streamlined by the time it gets 3 or 4 feet above the floor. It's triggered by this sharp throat, creates a whole bunch of vortices, and there's 3 bad things that happen all at once with this single choice of lousy fitting. Number 1, you have a huge pressure drop triggered by this throat, so there's a huge restriction of air. You have to use a lot of static pressure to overcome it. But imagine what's happening to the filter right now that you put between the drop and the furnace. Your filter isn't performing as it should because you're forcing all the air through half the area, which is a bad thing to do with filters. But secondly, what you're feeding into the appliance right now is a dog's breakfast of mixed air, so the fan in that furnace cannot perform to proper rating. So that one single fitting is slaughtered, and all by itself is the worst single fitting that you can do in a highboy furnace at a standard installation. And it's not very hard to get in there and actually measure. In this case, it's a temperature rise, but you can take static pressures and find out exactly what happens to each one of these fittings. In fact, with 10 minutes worth of work, you can determine exactly how good or how bad the ductwork system is without even seeing anything. If it's all behind gyprock, as a couple static pressure measurements will tell you exactly the adequacy or the total shortfall of duct systems in an existing home without even seeing one thing, without even looking how much plate's been cut out, which is the common culprit. Now, for nothing more than putting turning vanes in that fitting, 1.5 inch space turning vanes, that 50 feet of equivalent length, plus the handicap of the disturbed air you're feeding the filter, you can get your equivalent length down to 6 feet. So you got an 8-fold improvement on the worst fitting in the whole house for the price of a lousy few turning vanes put in carefully. It's really, really simple when you look at all this stuff. Why do we make an issue of that? Because the new appliances move a hell of a lot more air than the old one, especially if you go heat pumps. Number 2, people are starting to demand better filters. And if you start demanding better filters, you're going to have a higher degree of static pressure drop in order to get the filtering performance the public wants. So you can't put this kind of stuff into a standard system because you have gobbled up all your available static pressure from your plants, consumed in overcoming a shit duct system, so you get nothing left over for the benefit of cooling coils or proper filtration. We're getting into the whys of this. We spend a whole lot of time in talking about moving air up a wall cavity. And oval duct, of course, is bad all by itself. A 6-inch oval stomped onto a 3.5-inch drops it down to 5-inch. But the real penalty is by going through 2 of these fittings, you now have 149 feet of equivalent length. This isn't mathematical gymnastics. This is actual measurement. 149 feet of equivalent length to get air from the basement ceiling to the joist system in Mrs. Smith's bedroom 1 floor up. You've got to start thinking smart, because it all boils down to the fact that your heating appliances don't pack much punch with a CFM anymore. It takes a lot more air to do the same job as we used to do before. That's the whole story, but what we've been able to do is we're making an effort to get this course down to 2 days from 2.5, but to make sure that people aren't signing up with this thinking it's a cakewalk, Todd Backus, who is involved in the preliminary work of this revision, has created a mathematical tutorial, which goes through step-by-step, multiplication, division, squares and square roots, so you can understand the fan laws without getting overloaded with the fundamental math while we're going through the principles of moving air. That's it. Thanks very much. Oh, yeah. If you're interested, this being offered in Surrey, November 25, 26.
Any questions for David? Nice job there, David. Anybody got questions about Pullman?
There's been a couple of people here. Steve Thompson has taken it. Gary is obviously involved, and I know there's another person who was here that took it. Yeah, Jollymore, Steve Jollymore. Do you guys have any comments?
I just noticed it says November 25th and 6th, but I thought the flyer that I was given at the shop the other day was well after the 22nd, 23rd, Thursday and Friday.
I'll bow to the boss on that one, Steve.
Right? Yeah. So we were told 22nd, 23rd.
I'm glad you caught it. Thanks very much, and we'll correct that. Anything else, guys? Yes, Doug.
Dave, what I see on the field is 1 inch ceiling filters with no work rate on what would you guess them to be?
Sorry, say the question again, please, Doug.
Out in the field, I've seen a lot of 1 inch filters that are pleated.
Pleated?
But they have no work rating on them. I'm just wondering what would you guess them to be? I'm guessing 6 or 8.
Yeah, generally speaking, if it's not labeled, it's probably 6 or below. If they get 8, they get brownie points from, I forget the commercial program. They get brownie points for that. So if it isn't labeled, you'll find it will be below 8.
So if you see a 1 inch filter, wouldn't you encourage people to go for a lower work rating because of the static pressure across them?
Well, see, that's a trade-off. The finer the media you have per square inch, the greater the pressure drop. Typically, the higher MERV filters will be deeper, and there'll be finer pleats to try to combat that.
You know, those are not people that they go people sell something and I think per ones are 13, 15. Yeah. And like a lot of those guys are selling like this is better. They think they're buying a better filter because it's more expensive. But now they're dealing with higher static.
Absolutely, and what people don't understand is if you start adding static and you add a smart electronic motor, an intelligent motor, your electrical costs go directly up. Yes, Gary? Hell, we can do it all in math in 2 minutes. You don't need to study that shit. I mean, you can take the money. I don't want it. I mean, the fan laws answer all those questions. You don't have to study it. You have to just measure the existing system. You say to yourself, I want to add 0.2 of an inch for a higher MERV filter, and you can translate that in runtime per year in exact dollar and cents. It's very, very simple.
So what would you speculate then if you put in you're running static 3 on a brand new team? That's probably what filters do is like when they're clean, of course that's when they're versus when you get dirty, they're really well.
Of course. But your airflow will go down unless you've got an ECM motor that will ramp up in power to compensate for the loading of the filter.
Everything when you see them now, pretty much it seems like a high percentage of stuff I see is all this. So, I mean, that,
Everything we see in short there is the fan efficiency ratio just has to be less than manufacturers. We don't have to use much curve your input or have a better fan.
I wouldn't mind seeing something that told me what the increase in cost would be versus installed with static pressure versus one that's got all the things wrong.
Please go for it, Gary. Come up to the front so everyone can hear you and then scream.
The big deal is, I don't want to say ECMs are a myth. ECMs are fantastic motors for running at lower loads for long distances.
For electrical cost.
Commercial costs, they're a little different homes. If you run those down on low speed, you run, you can run that, you know, 100 horsepower motor down the front, so that you watch for 40 watts in minutes. PSC motor doesn't do that. PSC motor running in half watts, so it's operating cost of motor. ECM running constantly, constant first system in the house, see which calls are over. PSC. But you have a air conditioning system and all of the time for air conditioning system. The PSC motor, ECM motor, each of those running near their load or their sweet spot and not in the main operating range, you would argue that there's no saving cost.
I'm looking for those that when I see these systems installed, with high static pressure, not sometimes the house is shaking because they're ramping up, so the motor ramping up. What would be the electrical cost to run that motor at those static pressure versus?
Doug, you can't answer that because the electrical cost for heat or for cool depends on runtime. So there's no way you can answer that question unless you have a runtime or you have some other method of calculating how many hours of the year you're actually running at the heating or cooling speed.
And most manufacturers will have a table in this issue and there's a ceiling inputs and pressure drop. So you just put a pressure drop and the lots of pressure drops.
You'll be horrified if you look at those tables and you're running at 0.8 of an inch. Your wattage on those ECMs would be right through the roof.
That's what I suspect. I wonder if some of the complaints that people have about their high electrical bills going up. When they put in a new gas furnace, they're kind of wondering what's going on. The house is shaking, you kind of know.
Well, one last thing I'd like to leave you guys a reminder with. With every residential duct system, there are speed limits on the air through the duct. It's 10 miles an hour in the main trunk, and it's 5 miles an hour in the branch. If you break those speed limits, you will pay, and you will pay two ways. Mrs. Smith is pissed at the noise in her bedroom, and number two, you're spending more on electricity than you should be. You cannot exceed the speed limits because there are tickets assigned to you in complaints and electrical consumption when you go past that speed limit. Thanks, Scott.
Thank you, David. Oh, one more question, sorry.
What does that translate to in feet per minute?
Say again?
What does that translate to?
Multiply by 100, you get close. 10 miles an hour is 1,000 feet a minute. 5 miles an hour is roughly 500 feet a minute. All of our tables are based on branches at 500 and trunks at 1,000.
Excellent. Thank you, David. So I like the technical juice is flowing. That's why we're all here. Excellent. So we have, Chris, you can get ready if you like. Show of hands, anybody that's doing hydronics these days? Who's in the hydronics business? Show of hands. 1, 2, 3, 4, 5. Okay, all this forced air talk, I just want to make it clear that we're not forgetting about the hydronics people. There's been, in the past, some level of frustration.
Can't get a course at UCRT.
Take the course, can't get a course?
Can't.
Yeah,
It's been canceled the last 6 courses.
Yeah, so, yeah, and we have to do something about that now. We were just talking about that in the board meeting tonight. So what's gonna happen is we'll have to take control of the teaching just like everything else, ourselves, and BCIT as a delivery provider needs to make X amount of dollars, whereas, we can deal with smaller class sizes and so forth. So it looks like that's the way it's gonna go in the future. And we'll also expand what we offer with respect to not just hydronics designer, which is a little onerous if you're just curious about hydronics. There are in existence now some existing courses that have sort of an entry-level hydronics, which will try to round out sort of a course offering, if you will. Hydronic Guidelines 2009 edition was the last time we chatted about hydronics with respect to the guidelines. And Leo's over there going, yeah, time you guys did some changing, which we're going to do. And it's mostly around the primary, secondary piping arrangements. Since 2009, there's an awful lot of boiler manufacturers that have their way of doing things. You got your Beastmans, you got your IBCs, you got your Buderas. Everybody's got a way of doing things. With respect to primary, those that are in the hydronics field, primary, secondary piping systems. So we want to get everybody together and beef those guidelines up so that the manufacturers' methodologies are taken into consideration in our primary, secondary piping. Nowadays, of course, all your boilers do multiple temperatures. They're all condensing now. I don't know who's buying mid-efficient boilers and putting them in. So what we're going to do in the future is focus less on mixing downstream and more on primary, secondary drawing. So that's something, now that we got the code stuff out of the way, being F280 and we've got HRV good to go, okay, over to hydronics we're going to go. Just so you know that you guys aren't left in the dark. And Chris, looks like you've got HRV, speaking of which, to talk about right now. Christopher Daw of Energy One is going to get up and talk about the course that's developed for HRV. Chris, she's all yours.
Thanks, Scott. Okay, so yeah, I've been working with TECA over the past year on a couple things. Excited to show you everything we've been doing. HRV course, I'm going to talk to you for hopefully about 10 minutes. I don't know where we're at for time. And then F2A will be after this for 20 minutes and we'll do kind of questions as they come. So, the heat recovery ventilator design and installation course, we've held the beta for that, getting everything compiled, and we should be ready to go in October with launching this course. It'll be a one-day course, and as Scott was saying, it's going to be a stamped certification. This is what the manual looks like. So yeah, I'm just going to kind of outline the course for you, show you what it's all about. Basically, we say there's three main objectives to this course. First of all, what is an HRV? What is this appliance? All the functionality of it we go through. We talk about how to design a system. We want people when they leave the course, all right, you're contracted, go into this house, design a heating system, install it top to bottom. You know what you're doing? And the goal is to have people say yes when they leave this course. And then, obviously installation, commissioning, and balancing is a big part of it as well. So first of all, the HRV itself. One thing we want to really stress is that this is an important topic. Why is this so important? It can literally be as important as a health and safety thing, right? You got dedicated ventilation in a house and a bedroom's not getting any air. That's a big problem. So we want people to take it seriously for sure. Part of the course we do a pre-assessment, see where everybody's at. Always get some good conversation going. I think it was about an hour and a half of it in the beta course. But we do one of these at the beginning and then one at the end. And it's a great time for discussion. We go through the different defrosting methods of the HRVs. We've got fan defrost, damper defrost. Talk about the differences between an HRV and an ERV and when you might choose to do one over the other. We talk about the terms, the quality of these. We got apparent sensible effectiveness and we got sensible recovery efficiency. That is the one in the BC Building Code. So just getting people familiar with this appliance and what it's all In the BC Building Code, there are 4 different mechanical ventilation systems you can do, 2 of which involve an HRV. One is if it's integrated with a forced air, and then the other is if it's just dedicated ventilation ductwork. As you can see, we got the forced air integration HRVs in here, ties into the return trunk, obviously dedicated exhaust still, but supply is done by the heating system. The other system you can do is dedicated ventilation. So this is supply where you want ventilation air and exhaust from stable air sources. Go through everything again just to review it. HRV system design, this is based on checklists. We have a design checklist and an installation, commissioning, balancing checklist. This is BC Building Code stuff, and one thing after another, you follow it through. We've tried to make it very user-friendly. So as we go through this section, talking about how to design an HRV system, people are following along in their check sheets and making sure we're all aware of what's going on. We say that an HRV system design has 5 parts. Choose the HRV, and that's as simple as what kind of heating system you got. Okay, this is how we're going to do our ventilation. How much air do we need? What type of appliance do we need? We're going to lay out the duct, and we're going to size the duct. Very simple, and these are all outlined on those check sheets. So like I said, is it partially dedicated? That's if you have a forced air system. Fully dedicated is if you do not. The required CFM comes from the BC Building Code. There might be other requirements as well for fresh air to inhabitable rooms, but BC Building Code comes out with a number. You've got 4 bedrooms, 3,000 square feet, 75 CFM. That's your minimum value, period. Selecting your appliance, governed by a few things. Are you doing an ERV or an HRV? Most of the time it's an HRV is what we've been hearing. Static pressure, obviously, like David was talking about too, it's the governing factor. You make sure that your appliance can deliver the amount of air at this static pressure. And then a couple other considerations as well. Laying out the duct, we go through a few different methods you can use to kind of represent the duct system. This will be just over top of actual structural drawings here. You can do a schematic, or you can actually try to mimic what will be going on in the duct system by drawing a nice little isometric sketch. And then duct sizing. And then we review the whole section, and then we got installation here. Again, installation is based off the check sheets. We're not expecting people to remember everything. Lots of the governing factors in the BC Building Code are right in the check sheets. You just check it and move on to the next one. For example, we go through the insulation. We talk about the different times you might need insulation and vapor barrier. Go through the different scenarios here. Supply coming through an unconditioned space, conditioned space through the HRV into the home. And then the commissioning and balancing section. We're definitely going to be doing, a lot of this is in class, right? Lots of images and discussion. And we're also going to have at least a video for people to see actual balancing of this system. We'll go through the different tools you might use. Don't know if anyone's using this. But yes, this is a flow grid, good for measuring the airflow actually to and from the appliance. And then a flow hood, that would be for measuring like a diffuser. We say the steps for balancing. We got to prepare for the balancing. Make sure all your windows are closed and everything like that. Balance the appliance first, then we balance the branches, and we go through kind of a step-by-step of how this is actually going to work. And then at the end, there's a very big example we do. Typically, this is about an hour at least in class, where we actually go through and do this top to bottom in class. And then it's fun. We get to have a discussion of where you're putting supply and exhaust and why, and how much are you doing to where. And then, like I said, a video, and post-assessment of everything, exam, and then we're done. So that's HRV. I motored through that pretty quick. I don't know how we're at for time.
Questions, anybody? HRV course coming up. Anybody got questions for Chris?
I have a question. When you worded it there, it said balance the equipment first, and then balance the
Yeah, yeah. Right here?
I don't see the plans, and I don't see the images. I'm just wondering if we could go back and don't see the plans again.
Absolutely, and that's part of it for sure. These are the main parts, but that is definitely in it. Because when you balance one thing, it changes everything else, absolutely.
Are you gonna be talking about Vancouver? Is there a very different approach?
We don't tailor our course for Vancouver, but yeah,
Because isn't that part of competition?
yeah. Yeah, and we are working with the City of Vancouver on this specifically, and yeah, we're back and forth on the check sheets as well.
City was actually on the beta course, actually.
How would someone look for them to do an inspection for the system to balance and certain balance against?
Yeah, you measure.
Is there any documentation spots that we would,
Any documentation spots?
well, some write something on it, I don't know.
The checklists themselves have a literal checkbox for appliance and each zone getting proper airflow.
But even if you write down the first one,
Yeah, on the design sheet, you say how much you're putting to where, and then on the installation and balancing sheet, you check off it has what you.
I think Doug's more asking, is it stuck to unit somewhere?
Yeah,
Where's the
Have
unit?
like a sticker or something
There's a
like that.
sticker in every HRV or ERV that says what your balance is.
Right, right.
So, it's sticker you can be very
Okay, good question.
Chris, Doug's point is a good one, because City of Vancouver is basically piloting the requirements for HRV that are very likely to be used within the energy step code process. So there's an initiative right now that's being asked by the Energy Step Code Council for the technical committee to come up with some guidance around design, installation, and verification of all mechanical systems. We're starting with HRVs. And so it would be nice if there was some way of saying, rather than a checkbox, yes, you met the design intent, there was actually some numbers behind it.
Okay, I hear you. Yeah.
The most recent certification document that we checklist document. So actually asks you to record all the exhaust flows and exhaust regulations, all the supply flows. And the point of the checklist is to really do that field verification. So typically done by a standard third party, the installer, the screen version. But it's a step in actual documentation rather than before it flows, before it balances.
So I just want to emphasize the importance of this course, because it's obviously designed by industry, which is great. It's going to be asked for more and more in the near future. There's 13 municipalities that have already signed on to the energy step code, so they're, as part of that requirement, they have to show a mechanical design. They don't have to show a mechanical design. And this is required. Not there yet, but that's the process of being piloted in Vancouver, and then it'll be presented back to the energy step code council for their endorsement.
That's great. Thank you. I made note of that, and we'll discuss it for sure. Anything else? Yes, it was also decided today the TECA ventilation course is going to be a prerequisite to this course.
You know, we do go over some of the code, obviously you saw, with respect to ventilation and air change requirements, but it is not a ventilation guidelines course. There's many more things in the guidelines, ventilation guidelines, and we don't have time to go over it in HRV. There's 1,000 people now in this province that have ventilation guidelines certification. So I think we're safe to say you should have that as a prerequisite before you go into the HRV course. And make no mistake, the HRV course is not a ventilation guideline stamp. They're two different stamps.
Anything else? Yep.
So are the cities going to be requiring both the stamps on the checklist, or 2 different stamps?
Depends on the
So
state.
that'd be nice, because what I'm finding is that inspectors don't know what they're looking at. They just take that sheet, put in the paperwork, and that's the end of it. Guys like us, we go in, we do the job all the way, they don't care.
Right, right.
Other guys go in, we just write up a checklist from home and hand it in. So I'm wondering if there's some program where the inspectors are getting.
Maybe we're doing a lot of trained inspectors around the office.
Okay, because I did run into one inspector from, state West, who actually knew that he was looking at.
Yeah, we're doing
Screening us.
That's pretty short.
That was just their,
It's still-
they need their
It's
CPT
still a little-
Well, you know, with all due respect to the inspectors in the province, they've got a large amount of things that they need to know, especially in the smaller townships, municipalities where the building inspector has to do the ventilation, he has to do the plumbing and so forth. How many things can you know? And so I've actually said, you know, really what we have to do is get out and do the best we can with the municipalities and assist them. And I'm not thinking ventilation so much, although David's done a great job getting out to the municipalities and supporting that process. But hydronic guidelines and forced air guidelines, the more comfortable the inspectors are with their interpretation, and there's some municipalities that are absolutely on top of it, and other ones that need a bit of a refresher, just like everybody else. So we're making an effort actually now to go around the province. We've been to about 5 municipalities between last year at this time and now. But we've got a lot more work to do. We think it's our responsibility to get out there and help the inspectors the best we can. They got a big job to do, and I think it's up to us to. This is not about enforcement. This is all about knowledge. Everything we're doing is only about knowledge in our industry to make it better. There's no sense if one guy takes the education, understands everything, and the other guy doesn't, and they're holding different jobs. So we're trying to make a fair playing field for everybody. And we're not policemen, we're not inspectors. All we can do is train, and that's what we want to do. So not just train contractors, but also inspectors or anybody that really cares to know. Sorry, Chris.
Hey, no problem. What time do we want to finish up?
Yeah, we could do this 20 minutes.
Yeah, 20 is awesome.
And,
Okay, sounds good. Okay, so now the CSA F280. Yeah, so Scott said my line. I was gonna say, No, that's okay. I was gonna say, so CSA, you've made this big elaborate heat loss document. You know, why do we care? Well, it is in the building code, so you know, obviously it's very relevant. I don't know if anyone's familiar with the CSA document. You can go online to the CSA website. You can buy it for $244. But yeah, so anyway, it's in the BC Building Code. We wanna help people adhere to these standards. We want to make it easy for people to do. We want to make it affordable, fast, and obviously accurate.
What's
So
the difference from what we do now?
extraordinarily different. Like, for example, if you're going to do a CSA F280 12 heat loss, you can't do it by hand. You need their software. CSA has special software. Sorry? Yeah. So I've kind of broken this up into 3 parts here. I want to give you an idea of what the CSA F280 is for exactly that reason, so you guys are just familiar with what's going on here. Some of you might know already. That's awesome. I'm going to talk about the TECA software that we've been making, and then I'm just going to go quickly through the values we're getting out of this compared to some hand calculation, just so we all have a little peace of mind here. I should just clarify, there's CSA software and there's TECA software. So I'll get into it, but CSA, so CSA has hand calculation methods and software, right? But TECA said, hey, let's take everything they do and make it one nice, clean software. So we'll get into it though. In the CSA F28012, basically they break up the heat loss in the different components, as I'm sure you're all familiar with. You know, it's kind of arranged like this. We got heat loss above grade conductive for the room. That's kind of how all these subscripts work. So you can imagine below grade conductive for the room, air changes, ventilation, ducting, and piping. So these are all the different components of a heat loss for a room. Heat gain, very similar. Conductive through opaque building assemblies, through walls and ceilings. Conductive conductive and transmissive through, obviously, you know, windows and everything. We got sensible heat gain due to people, due to lights, appliances, electronics. Sensible heat gain due to air leakage, due to ventilation, and due to ducting. So I just want to give you a little bit of familiarity with these terms here. And basically how it works is you sum up all of the heat loss of the rooms, and that's the heat loss of the building. And similar for heat gain, you sum up the heat gain, that should be a G. You sum up the heat gain of the room, and that's going to be, of all the rooms, and that's going to be the heat loss of the building. Internal loads do not get cumulatively added room through room through room. You need to make sure they're added to the overall building load once so that the heating or cooling system can handle it. And then, you know, you make sure the distribution to each room can also handle it if people are in the family room, and they're in the kitchen, and they're in the upstairs living room, whatever. So that's just a little bit about how it's arranged. They give you a whole bunch of formulas that look something like this. This is how you calculate heat loss above grade conductive through any building element, right? Whether it's a wall or a window or whatever. You got the area of it, the thermal resistance of it, and the temperature difference across it. That's one kind of difference you might notice from the old methods. There's no more heat loss multipliers, heat transfer multipliers, nothing like that. We're directly measuring the temperature difference across every building element and getting the heat loss through it. Simple as that. Well, no, it gets better. So CSA says, okay, here's all these formulas for how you do that. Sorry, I should say this is one of many different formulas. That's just how to do it for above grade conductive, right? There are more formulas.
Do you got the below grade on there?
The below grade is what was your question?
We don't have to know all these formulas.
You don't got to know a thing. Yeah, just, you know, rest easy. These are the CSA tools. Remember I said there's CSA software, TECA software. This is the CSA software. This is for below grade elements. So basically any element that's in contact with soil, you punch in all your inputs here and CSA gives you the load. Same with the slab on grade, obviously that's an element in contact with soil. These calculations you cannot do by hand even if you wanted to. They're based on, you know, corner correction coefficients. They got 145 different foundations that all have hundreds of coefficients behind them. So when you do a calculation by one of these tables, it's pulling from table after table after table. Same with the air leakage. So basically we want to determine how much natural air change is our building going to have. So you put all of your inputs into here again, and out come your natural leakage rate in air changes per hour. So for heating, for this example, we got 0.1 air changes per hour of natural ventilation. Sorry, natural infiltration. So like I said, we see all this CSA stuff over here. We thought, hey, let's take all of this and just plunk it into one nice clean formula. No math for anyone, you just punch in the values, that's it. So I want to get into that now using the actual TECA software. I've done up a little model home here. Just so you have some idea of where we're going when I'm going through this program. This is what we're doing. We're speccing this model house in the program. So basement, main floor, upper floor, you know. I know you're thinking like, you know, gosh, Chris, what a floor plan. Where do I get a floor plan like that, right? Okay, so yeah, and I also specify the construction of it, right? So the wall type. These are CSA pre-specified assemblies and everything that I'm listing here. So we got a wood frame with wood, vinyl, or metal siding as exterior cladding, glass fiber bats, 6-inch wall cavity, and lumber sheathing. Just an example. There's many you can choose from. The thermal resistance of this you don't have to know. You punch in your wall type and your sizing and everything, and we will spit you out in our value. So again, this is just to show you what the house is made of. Below here we have the foundation. wood floor, wood walls, exterior surface insulated to R20, blah, blah, blah. Okay, so I want to actually show you the software live now. I'm going to have to just go right here, I think. So keep in mind, this is minimum half day. We're thinking probably a full day course for this, so don't worry if you're not really keeping up with what's going on in the software. You don't have to do one yet. We're going to be selling it either as a part of a course or online with a very, very thorough tutorial of how to use it. Okay, so I just want to show you firstly, you buy new software, and this is what it looks like, right? So there's a couple things you got to go through here. You can see this up top here. Active content has been disabled. You got to enable the content. Anyway, this is for activation. So once I'm done these steps here, I click next. Now I'm going to register my software. So software number, a whole bunch of 7s. Username, Donald Trump, company, undisclosed. Okay, so that's what we're going to do. Activate software. Are you sure this can only be done once, right when you buy the program? Yes, that's what we want to do. Okay. Here we go. Now we're on to the TECA software here. Is that this little blown up, or do you guys want it in or out? Like, is that all right? Cool. So these are all editable fields, your date, drawings issued for, your name, everything like that. These down here, you'll notice I can't even click on them. This is your registration information. It's locked. It's very important when you're submitting one of these heat losses that people know where it came from, right? So this registration number is going to appear on everything you print out. I'll just skim through here, show you a couple things. For example, environmental conditions, you just choose where you live. Simple as that. Does the building have cooling? Yes or no? If it does, punch in your temperatures. This is for air infiltration. You punch in your building site location. How heavy is the shielding? Air tightness, for example, you can pick from one of the 4 predetermined values that differ significantly. Or, let's say you had a certified energy advisor on site and they did a blower door test. You can say, okay, I have my values. I know what we're doing. So you actually just punch in your information right here. But for now, we'll leave it as that. Ventilation. Do you have mechanical ventilation? Check or no check. How much do I need? Well, you might know it or you might not know it, so you can just look at the table. What's this? TECA. Yeah. So that's how it kind of works. You specify kind of the system of the building. You get down here, now you need to talk about construction, right? What are our walls and ceilings and windows made out of? What do they look like? So I've done these already because it's a little bit time consuming to go through. But you can see I've defined one wall type, that's W1. I've successfully defined one type. I can have up to 4. So let's say I want to add a type, okay? Add type. There's a few different ways you can input as per CSA. Let's say I know I've measured my wall, I know what it is. I can just click known thermal resistance and I can just punch it in. Name, thermal resistance, and RSI or R value. Simple as that. Or I can click select assembly type. So wall name is wall. Uninsulated wall assembly, you choose your type. Insulation, choose your type, choose your thickness.
It's the effective on.
Yes, exactly. So this takes into account framing, spacing, everything like that, based on predetermined values. Obviously, custom framing and everything can change things. But like I said, sorry. What you would do is you'd have to do the measurement on your own. You could use this as well, and then just enter a manual. Yeah. So yeah, you got wall, ceiling, floor. Okay, I want to do another window. I got one window type. Okay, add a window type. Do I know the properties? Or select construction type. Okay, double glazed. What's the framing spacing, and so on. These are all CSA kind of preset little selections you can choose from. Foundations. This is a big one here. So you specify the construction material and assembly type, and then you scroll through these different insulation selections, right? So you can see this little icon changing here as I go through them. That allows you to specify exactly what type of insulation and construction you have on here. And then over here, you just type in what your insulation value is. below slab, and the interior wall. Save inputs, and then you're done. Go to the next section. So what we've done there is we basically said, this is the guts of the house. Now we're on to the floor plan section. This is where you say how big it is, where it is, everything like that. So you got floor area, volume, number of rooms. This is kind of part of the tutorial. I'll just show you though because it's relevant. There's a few different types of input. A yellow box is where you just type in. That's just for like the name of the room. Numeric input is where all you're entering is a number. Code input is where, as you saw with W1, that's our wall 1. So whenever I want to say this wall is wall 1, I just type W1 in the green box. And then gray cells are locked. They're just for reference. So you'll notice up here, I've got this kind of locked header here. This is just to kind of remind the user of all the values they can use, right? So along the bottom, for example, you'll see here, defined construction element types. So if I've successfully defined one wall type, it's going to say walls, W1. I can use W1. Windows, window 1. Skylights, sky 1. So it's just showing you how a reminder of the inputs. The same with the units. Back here we selected the type of units, imperial or metric, right here. So if I come over here, the units are going to say, like we selected imperial, so it's feet squared, BTUs, and CFM. But if you selected metric, it would be meters squared, watts, and liters per second.
Are we still doing it by right?
Yeah, so we're coming to that right now. After this. So the last thing I want to talk about, window overhang shading. This is something that we can specify now. Just based on this little simple dimensional drawing here. We have 4 different properties you might enter. Most of the time you're leaving them blank because there's nothing, right? But if you ever want to enter it, you specify the overhang, the drop, the height of the window, and the width of the window. That would be kind of into the wall there, and it'll measure the shading. So, as you asked, room by room input. First thing we're going to do, what is the front of our building facing? It's north. You can change that at any point and it will adjust everything. This is an example room just to show people how to input. So floor level 2, is it above grade or below grade? Above grade. And remember, let's say you don't know what to type. Well, it's up here. Above grade or below grade, right here. Your room type, living room, bathroom, whatever, your floor area of the room, temperatures, radiant heating, ducting, all the different things you can specify. Lots of it's going to get left blank. And then here, for every room you have up to 4 walls, and is it exposed? What wall type is it? Remember we talked about wall 1, we've specified the area, the length, the door type, the window type, the overhang. So that's kind of what a room looks like. Down here I've done the first room. It's a foundation. Remember, so this is, that's my bad. I kind of jumped the gun there. This is for above grade and exposed building elements, all of this. And then right here, this is for below grade elements. So we have a foundation room. We leave all this blank, for walls and everything. Obviously, windows are still an above grade element. And you just type in your foundation type, your wall height, depth below grade, length, and exposed perimeter.
With the other basement wall that's not foundation, not
Yeah, so this came up recently. So basically, the below grade is for an element below grade. If you've got a concrete foundation wall coming up a foot above grade and framing on top of that framed wall is an element above grade. So you would specify in here whatever framing you have above grade. Yeah. And in the case you're talking about, it would have inputs for foundation and inputs for above grade. Because that wall is above grade. Are you guys following here? Am I going too quick? Is that all right? Okay. So yeah, I won't spend too much time on here, but basically once you do the calculation, over here, it has all of your values for heat loss, cooling, and also any warnings. If you input something wrong, it'll spit out a warning here. And so all the different rooms you specified up to, I think we got 8 here. So yeah, 8 rooms. And last but not least, we got the results page. As you can see, this is all locked, right? Because it's an activated, a registered program here. That's my registration number, can't change it. Very important part of a heat loss is that you show people what the inputs were, right? There's a million things you can assume all day long, and you can get significant changes with this. So whenever a heat loss is submitted, it's important that the construction and everything comes with it so people know what it's based off of. So that's part of the printout. If you ever want to print something here, it's got predefined print areas, and we got 4 pages here. And right here, on the second page, this is a summary of all the construction. Remember we talked about walls and ceiling types? That's all right here, literally typed out.
Is there an input for a client to come to another bureau?
You would, there's additional heat loss or heat load for each room, so you'd have to do the measurement yourself and punch it in. You're talking about for like assuming construction types and everything?
Say you go into a house, you're doing a furnace.
Yeah.
You go into
That's up to you, right? This tool does what it does and it lists everything. Let's say you assume the walls are R20. You just input a wall type and call it R20.
You're more likely doing a block load in that case as opposed to a room by room. Sorry? Well, yeah, it's the same sort of idea, in fact. So all you're doing now instead is just one block load. So we treat the whole structure. I would imagine anyway. You certainly could do a room by room. I don't know why you want to unless you're changing out all the duct to each room.
Yeah.
You really
And
just want to know the heat loss of the house. And that's the whole point, really, of F280 is they really just want you to identify the heat loss of the building and match your appliance to that building. So, and for their committee, correct me if I'm wrong, but really we just want to identify the block load of the building when we consider changing.
Yes.
Right.
But if you, one question is that where you agree, is that if you know there's an energy visor, it's pretty much already done.
Mhm.
You can just ask if there's an energy visor, it's already done the modeling, and you have that block load.
Well, it's rather easy. Or whatever, so we go do it, review it ourselves.
Well, I know like Vancouver, it's pretty much every house that has a combination of functions.
Well, when he says re and re, he's talking about just changing the furnace out.
Yeah, I
Not
know.
a renovation of the whole
Yeah.
building.
I know.
Just the heating plant.
But you would have that block load of that house, what I'm saying, with the energy evaluation of modeling.
Well, there wouldn't be there'd be no evaluation done. My furnace is broke down. Really what we need is a new one. Let's not
Oh,
fix
I
this.
see, I understand.
No, we gotta put a new one in. Chances are whoever put that one in 22 years ago,
Yeah, okay.
let's just look at the house again, do a block load quickly,
Yeah.
and say, oh, okay, really, we need 60,000, not 100,000.
But yeah, you can call it 3 rooms. Yeah.
Usually we play this part to see what the infiltration you don't know if that's the one. You just verify that.
It is, because yeah, like we said, you're selecting an air tightness level, and they vary a lot, right?
So what, have you played with that to see how much that would be?
Oh yeah, for sure.
The CSA version, and stop me when I'm wrong, but the CSA version offers some pretty generalized air tightness versions, and they're pretty dramatically different. Or if you had Scott come over and do a lower door test, then you could enter his number.
People that develop from somebody else that was involved in some of that was that in Ontario, when there was a building in 2000, these builders that had been verified before the door test, and they know they're building that, so when you get heat loss done for the plan, they already know what they're targeting filtration.
And the target, that's exactly it.
If
Yeah.
you have that already, it's beautiful.
Yeah, so I mean, they know, these builders know with some certainty that they can repeat this process over and over again, so they can actually specify that they
Yeah.
have it. And that was the intended use, was for you to put that rate in, the other ones were just as a guide, but unfortunately, I think the guide is what most people
Mhm.
they do very quite well.
Yeah, it's just bizarre.
Yeah.
That's a CSA product, so what do you do with that? You have to use a methodology. So, no,
But yeah,
it's great.
the directionality of it is yeah, like you said, here's what you need to hit because that's what it's all based on, and then you walk around and fill holes till you hit it.
Well, that's the same receptacle, usually if
Mhm.
you're looking at a specific irrigation.
Yeah. Cool. So yeah, just again, like this was a lot to go through. But yeah, so you got the construction page, right? This is all of your wall types and ceiling types and everything like that. You got the floor plan, that's where you actually enter in the room by room dimensions of this whole thing. And then you got the results page. Here's your building loads. We do a nice little chart for you, specify the general building loads here, and then room by room loads of each element all the way through. And that's what it looks like. It's a 4-page print. I have one printed out if you'd like to see it. What's that? Yeah, so, yeah, I'm going to get to that as well. Yeah. As of right now, it's spitting out heat loss. But yeah, obviously part of it is going to be CFMs or hydronic specs. So, if I come back here, where are we at here? Yeah, okay, we're about there. I was going to zip through, I did. Yeah. I mean, hey, if we're done, we're done. I spent some. I'm choking it down because I spent a good time doing a full by hand CSA heat loss and comparing all the values. But if we're out of time, we're out of time. I can take 30 seconds here. Okay, foundation loss, 695 is what comes out of the CSA tool. Watts, transfer to BTUs, 2372, 2372. There we go. That's what comes out of the TECA heat loss. For example, I did the by hand calculation of heat loss through a wall, 1002. TECA spits out 1001. Heat gain, this is incorporating solar correction factors based on the direction it's facing. 31, 6.3. Through the other wall, we got a west wall now, different solar correction factors, 67, 10. Add them all up, you get 114.8. Come here, got 115. What was that?
Where does it show on that sheet? Okay, you're punching in how many CFM reverse size in TECA, the one we use now.
Great. This heat loss is going to be the beginning of both airlines program.
No, I'm talking before there.
I understand.
Yeah,
That's
so-
the next step. You're on to the next step. When you're done with your heat loss, then it'll go to the CFM.
Yeah. Anyway.
What he's just going over now is we're just sanity testing. The longhand version, thank you very much. You can use all the do the longhand calculation, use the CSA software, and use the TECA software. So we're just going over the results to make sure we're on target on some of the results.
Yeah.
I think that's what you're doing.
That is, and yeah, if I need to stop, then I can stop.
Okay.
That's pretty much I go through more, but yeah.
Okay. Any questions?
Yes, David?
Compared to methods we may use today with gearing-based software, how is your number come up to his on an average house?
That's a good question that I don't yet have the answer to.
I'm weighing the answers that you could have given me on that versus how much time does it take you to do a takeoff and how much time does it take you to load that square footage, windows and all that into your software. So what is my total net time from the time I'm given a set of plans until I get a furnace sizing of it?
Great question.
It's like, is it an hour or is it a day?
It's not an hour and it's not a day. It's in the middle.
Yeah, it depends on it.
Yeah. I mean, a thorough takeoff of the whole set of drawings and everything, call that an hour to actually write down everything you've got, and then, yeah, maybe 2-3 hours to input everything and make sure you're correct.
So a total of 4 and down.
Maximum, I think, yeah.
You're talking about like a 3,500 square feet.
Yeah, I know, right?
It's
This is actually a lot more work doing a heat loss than it was with our TECA one we use now.
It is, for sure.
It's a lot more, it's gonna be an hour.
Yeah. I mean, there's more to it. There's more to it.
Thank the good people at CSA.
Yeah.
I think you should be ready for the question because we're paying more in time to do it. But a damn good answer is how much improved accuracy we get for all the extra work.
Okay.
I know that there's quite a difference between 1990 versus 2012 and the numbers that came out of it. Building knowledge did a lot of work on this area. And the foundation difference, so it's
Yeah. I think it's I mean, I've flown through it and it's a lot visually, but like I did the CSA by hand method. That was almost a day. And then I threw all that data straight into the program in under an hour. So it's quick once you get the hang of it, for sure.
Well, I would bet that 99% of the people here don't have the math skills you have. So the manual method is off the table. The real issue is the time it's going to take versus this and how much improvement we get. Even though, yes, you have to today because it's buildable.
I think the bigger picture is in the future as they start trying to build stuff, even looking at it like we're building right now, this is the only way that you're going to get the accuracy to actually start having little micro loads and some little mini splits and things to pull up as they get closer and closer to these passive houses to the poles. That the old systems would never, they just didn't have the detail level to be this accurate.
If you did on
In a year and a half, they were
The other thing that they take into consideration, people who look at the gas fireplace, so it's not being taken into consideration on heat loss.
That's part of the appliance selection side of it. Heat loss is a heat loss. Is that what you're asking?
Can we use in the new method, use fireplaces for the heating appliances for the house?
Yeah, you can specify additional loads if you know what that fireplace is putting out.
But the BC building code does require adequate heat in every room to match the loss of that room. So a single central appliance would not meet the requirements of room-by-room distribution that the code calls for elsewhere. In other words, if you're putting in baseboard, radiant floor, forced or whatever, every room that has a loss needs gain. Can't argue with that either. Heaven help you if you don't heat bathrooms.
Well, we used to do a renovation in Surrey, and they called it a mechanical engineering to the heat loss. I think it's actually heat loss, and I had heat in every room in the house. The same air come in and said, well, because it's an interior condos, she says we didn't need heat in the bathroom, or walk the closets, or a powder room, or any of this. This house ain't going to heat.
Well, if it's a top floor, you don't loss upward. If it's a middle floor, 2 levels, it's a powder room, there is no loss.
No, but she had 1 6-inch run through the whole main floor, basically.
Sounds like a piss poor way to do business.
So the engineer called.
Any other questions for Chris? Thank you, Chris. Nice job. Chris?
Here, I'd just like to give you this as a little dedication for us.
Thank you very much. So when it comes to that software, the question was asked, and we never answered you, about where's my CFMs? All I want to know is the CFMs. I got to run CFMs to the room. 100% right. So it's not a stretch from there now that we know BTUs per room, turn those into CFMs. So that's where the existing duct design software will integrate. So now we have this software to sit on top of the existing duct design software, and it'll tell the BTUs to the duct design software, which is going to have the CFMs. Similarly, on the radiant side, I mean, what is it? It's flow and delta T. So you're going to select your hot water side or your forced air side. Forced air side, I mean, we can do it now to just have CFMs if you know where your delta T is supposed to be based on your appliance. So the hard work, the heavy lifting is done now with the F280 to integrate it. So now it's just dropping it on top of the existing software. Anybody here do hydronic heat loss calculations? Anybody? Oh, here we go. Come on. Heat loss is heat loss. Oh, okay. Let me be more specific. Anybody here doing hydronic system design, starting with the heat loss?
Of course.
Okay, we got one guy. Do you mind if do you use a program?
I use the old
Thermally?
first sheets out of the manual from 5.
Nice. That's all
And
right.
I've transcribed that into the spreadsheet, which
Okay. Anybody else? Heat loss using, what's everybody using right now for forced air? Heat loss is the same, but forced air duct design or otherwise, people using the TECA? Okay, good. Yeah, I think that's most common. Yeah, and when it comes to CSA compliant, there's only really 2 softwares out there in North America that are F280 compliant. So, and they're a heck of a lot more money than what we'll be selling it to you guys for. Again, we're a nonprofit. It's not about making money. It's about getting you guys educated and doing what you need to do. Thanks again for your time. I hope you guys learned something. I certainly did. I appreciate everything that was done today by David Hill and Christopher Daw. Engineers Talk. So I saw you guys with when the formulas went up. I swear the room just kind of clenched a bit. It's really not that bad. It's all taken care of. Again, thanks again for coming out tonight, guys, and we'll see you next time. Thank you.